In this video, I'll talk about the sign test for the median. So for this example, we have 10 measurements of weekly sales of potato chips. And our hypothesis test is that the null hypothesis is the median is 450, and the alternative is that the median is greater than 450. So we're doing an upper tail test. And so I've written my hypothesized median here. Our sample size is, we have 10 measurements. And with the sign test, we throw out any measurements where the sample value is equal to the hypothesized median. But in this data set, none of these values are equal to 450, so we have the full sample size of 10. We could think of this as a hypothesis test about a binomial probability, P, and the null hypothesized value is 0.5. Our test statistic is simply a count of the number of sample observations that are bigger than the hypothesized median, 450. So that's what this function does here. It counts the number of observations bigger than 450, and there's 7 of them. And then we can think of this as an outcome from a binomial experiment with sample size 10 and probability of success 0.5. And so the p-value, given that we got a test statistic of 7, the p-value is going to be the probability of observing 7 or more successes in such a binomial experiment. So 7, 8, 9, or 10. And to calculate that, we can use the binom dist function, and we can just check what the arguments are for this function using the formula builder over here. So remember, when we looked at the binomial distribution before, the first argument is the number of successes. So that's the test statistic here. But I'm actually going to subtract 1 here, because what I'm going to do is I'm going to use the cumulative distribution function to figure out the probability of getting up to 6 successes. And then I'll subtract that from 1 to find the probability of 7 or more successes. So that's why I've subtracted 1 in here in the first argument. And then the second argument is the number of trials, so that's 10. The third argument is the probability of success in each trial, and that's 0.5. And then the last argument is going to be true because we want the cumulative distribution function. And as I say, if I subtract that probability from 1, I'll get the probability of 7 or more successes. And that's the p-value for this hypothesis test. So that comes to 0.1719. If we're using a significance level alpha of 0.05, then we will not reject the null hypothesis, because as usual, the decision criteria here is if the p-value is less than the significance level, reject the null, otherwise do not reject the null. And 0.1719 is not less than 0.05. So we do not reject the null in this case. So that's an upper tail test for this example. If this was a two-tail test, then all these numbers are the same. The first number that differs is the p-value. And because it's a two-tail test rather than a one-tail test, the p-value is simply 2 times the one-tail p-value, the upper tail p-value. So that comes to 0.3438. And again, the decision is to not reject the null hypothesis because this p-value is bigger than the significance level alpha. Let's look at another example. So in this example, we have sales prices for homes, and our hypothesis test, this is going to be a lower tail test. The null hypothesis is that the median is greater than or equal to 236,000, and the alternative hypothesis is that the median is less than 236,000. So it's a lower tail test because we have a less than sign in the alternative hypothesis. Our sample size is the number of data values here minus any that are equal to 236,000. And we do actually have one in this data set. So brings the sample size from 61 down to 60. Our hypothesized binomial probability is 0.5. And our test statistic counts the number of sale prices that are greater than 236,000. And there's 22 of those. And then the p-value. So the p-value, because this is a lower tail test, we need the probability of observing 22 or fewer successes in a binomial experiment with sample size 60 and probability of success 0.5. So we use the binomial distribution function with the first argument, the number of successes equal to 22. I don't have to subtract 1 this time because I'm doing a lower tail test and I'm finding the probability of 22 or fewer. And this function will give me that directly. I don't need to subtract 1 or anything. I'll subtract this probability from 1. And then sample size 60, probability of success 0.5, and we're doing a cumulative calculation. So that comes to 0.0259. And if we do this test at a significance level of 0.05, we will reject the null hypothesis because 0.0259 is less than 0.05. If we did a two-tail test here, okay, all these values are the same. The number that differs is the p-value, and it'll be twice the size of the p-value for the lower tail test. So it's actually 0.0519. It's bigger than 0.05, so if we were doing a two-tail test here, we would fail to reject the null hypothesis. Sometimes with a large sample size like this, n equals 60 is relatively large, rather than using an exact binomial probability calculation, people will do a normal approximation. And so that's certainly possible to do here, but given that it's easy to calculate the p-value or have Excel calculate the p-value for you, I don't see much point in doing that normal approximation. You might as well do the exact binomial calculation. It usually leads to the same result in either case.